Iniziamo? Finiamo un po' prima, io sto dormendo. Voi avete fatto traduzione? Okay, so just a reminder what we left on the other side. So from last time we had rate monotonic as a scheduling algorithm. Fixed priority proportional to the rate of a task. So the higher the period, so the longer the period, the higher the rate, the lower the priority. The higher the rate, the smaller the period, the higher the priority. So this guy with a small period has high priority, large periods, small priority. Test for checking the utilization and the feasibility of a task system with a rate monotonic. We would like to check, for instance, the utilization of a task. Utilization defined as the ratio between worst case execution time over a period. We sum the utilization of all tasks and we call that system utilization, okay, or processor utilization. We would like to check if there are task systems schedulable with utilization greater than 1, smaller than 1, smaller than a given bound. So we for sure can say that utilization greater than 1, we said, leads to an infeasible condition. So I cannot allocate more than one processor, okay, if I have one processor. If utilization is less than 1, there are cases in which a task misses the deadline. We saw it last time. So this utilization is 0.9 something, is less than 1. Still, I have a task missing the deadline here. Okay? Instead, we have other tasks with even smaller utilization, which are schedulable. Okay? So it's difficult to understand what is like a good bound for a utilization. Okay? For instance, this task was a task barely schedulable. We call it barely schedulable because just a tiny bit more of execution, either here or here, would lead to a deadline miss. Okay? So this 0.833 seems like the best I can do with a task of this kind. Okay? The utilization I have there seems like the maximum one I can obtain. But there are other cases in which I can reach 1, the utilization, and still have a schedulable situation. Again, 2 tasks, but in this case, I have a schedulable condition. So I'm interested in checking the utilization of tasks that are barely schedulable. So all those task sets that increasing an epsilon more would lead to an unschedulability condition, so to an infeasible setting. So here you can see there are various tasks. I'm interested in finding what is the lowest utilization for which I have a schedulable task, but increasing an epsilon more in the utilization would lead to an unschedulability result. Okay? So we're interested in understanding what we call a utilization least upper bound, okay? So that if my task system will have a utilization smaller than that bound, then I can declare it schedulable. If it is above that bound, it doesn't mean that it is not schedulable, okay? It means only that I'm not able to check whether it is schedulable or not based only on the utilization. Okay, let me repeat. So the least upper bound, so we have cases in which we have, so the utilization, okay? Utilization, if it is greater than 1, okay, here increases. If it is greater than 1, for sure it is not schedulable, okay? Then I have a utilization least upper bound, okay, which I know all task sets which are around here are for sure schedulable, okay? So task sets which have a utilization smaller than this least upper bound are for sure schedulable. Task sets which have a utilization between this least upper bound and 1 I just don't know. So I cannot discriminate the feasibility of those task sets only based on the utilization. Okay? So we will see that we have better tests that allow us to discriminate better this gray area. Okay? Today I will show you a utilization list upper bound, which is only depending on the number of tasks I have in the system. Okay? If I would like to discriminate better the region of feasible or non-feasible task sets, I will need to use something smarter than the utilization itself. Okay? For now, I'm just giving you a way to compute a list upper bound. Okay? So we know that the utilization is smaller than the list upper bound. The task set is for sure schedulable with rate monotonic. Okay? Tasks instead that are in between, we just don't know. Okay? We don't know whether they're feasible or they're not feasible. So this is the list upper bound for rate monotonic. One of the list upper bound. I can compute a list upper bound for any task of any dimension. I can compute a list upper bound if I know the information on the number of tasks that are in my system. Okay? So in this case, I exploit the information on the number of tasks. So assume you have n tasks, then you can compute a list upper bound for rate monotonic, which is the one that you see in the formula. Okay? So n times n squared of 2 minus 1. Okay? So what does it mean? That this is like a bound that decreases the greater is n. So the bigger is n, the smaller this bound. Okay? So if n is small, this bound tends to increase. When n is 1, what is this bound when n is 1? When n is 1? 1, okay? So, of course, if I have just one task, when it isn't schedulable, when its utilization is at most 1, okay? When I have two tasks, this goes to twice square root of 2 minus 1, okay? Which is 0.80 something, okay? So with two tasks, I'm around here. With three tasks here, 4, 5, 6, 7, 8, 9, 10. With infinite tasks, these approaches, you can do the limit. You're engineers, you know how to do that, right? And it approaches logarithm of 2. Okay, this is about 0.69. Okay, so this is like a list upper bound when I don't know the number of tasks, or the number of tasks could be infinite. Okay, so when the number of tasks, either I don't know it, or it can be infinite, okay, or it's very large, then it approaches logarithm of 2. So here is basically the function depicted there. So with 1 is 100, with 2 is 80 something, on and on and on. Already with 8 or 9 tasks, 10 tasks, I'm approaching the logarithm of 2. Okay? So with 10 tasks is about 70%, a little bit smaller than 70%. Okay? So this means that with rate monotonic static priority schedule algorithm, actually the best static priority assignment I can use, I'm not allowed to schedule predictably 100% of utilization if the number of tasks in your system is a little bit higher than 1 or 2 tasks. Okay? So this means you're not able to fully utilize your processor while guaranteeing all the deadlines. You have to sacrifice workload for predictability. Okay? So this is essentially the test. Okay? It's a test where we first compute the utilization in my system, and then I check this inequality. Okay? What is the complexity of this test? Given, okay, you didn't do algorithm. Anyway, this is like linearly computed, and this is just a sum of n terms. Okay? Very easy. It's either constant, or you just compute you assume to having to compute n factors there, then it's n, but it's a constant complexity. Okay? It's a constant complexity. It's the simplest test you can do there. Okay? It's just computing the utilization and checking against this value. Okay? And if you don't know n, This is just 69%. Okay? 69%. So, how do we check a better test? So, I told you, I gave you a list upper bound here. If you're fine with that, and your task is below this list upper bound, your task set, then you're fine. You're schedulable, okay? If you have a utilization above 1, then again you're fine, it is not schedulable. You're sure that it is not schedulable. If you're around here, what can I do? Let's find out a better test than something that is just based on utilization. I didn't provide you the proof of the utilization bound, okay? The proof is in the Liu and Leila paper that I pointed you before, okay? It's a little bit complex, nothing special, but for those of you which are interested, you can take a look at the paper. And it provides you a way to compute this sufficient schedulability test. We call a schedulability test sufficient when, if it provides a positive answer, the task set is for sure schedulable. While if it provides a negative answer, I don't know anything. Okay? This is a sufficient test. Repeat, a sufficient schedulability test means that if you pass the test, if your task set passes the test, it means that the task set is for sure schedulable. So passing the test is a sufficient condition for schedulability. But not passing is not a sufficient condition for inschedulability. Okay? So this is a sufficient test. A necessary schedulability test is instead, is U below 1? Okay? If it is above 1, then for sure it is not schedulable. But if it is below, I just don't know. Okay? This is a necessary test. Okay? The best thing to have is a test that is both necessary and sufficient. So necessary and sufficient test will be able to discriminate properly also this area here around, okay? Dividing what is not schedulable with what is schedulable. Okay? Necessary and sufficient test. So passing the test means schedulability, not passing the test means non-schedulability. Okay? I will show you a necessary and sufficient test which has a slightly higher complexity than the utilization-based test that I just showed you. So here we have two tasks, okay, two general tasks. To derive an exact test, so a necessary and sufficient test is also called an exact test. Okay, not that the sufficient tests are wrong, okay, just when it is both necessary and sufficient, we call it exact. Okay? So to determine a necessary and sufficient schedulability condition, we would be interested in knowing what is the worst case situation that can arise between two tasks. The worst case situation meaning what is the particular interarrival of tasks that would lead to the larger response time. So here we don't have just one jobs. We have periodic jobs, right? Which are repeated at periodic intervals, okay? Assume for now strictly periodic tasks, okay? Strictly periodic tasks. But we have two tasks and they may arrive in different manners, okay? I don't know how the radar will be sampled or the camera will be sampled or the inertial motion unit will be sampled or the operating system call will be sampled. So there can be different misalignments between periodic tasks with different periods. So I'm particularly interested in understanding which one of these interarrivals will lead to the larger response time. For instance, with this kind of arrival, you can check the lower priority task will be preempted twice and it will finish here, okay, with this response time. While if both tasks start together, okay, it will be interfered by 3 jobs of tau 1. Here just by 2, here by 3 jobs, okay? And the response time is larger. The response time is larger, okay? So we are particularly interested in determining the worst case setting. We call it critical instant. Critical instant means the critical scenario that leads to the worst case response time of one or more tasks, okay? It can be the same scenario leading to the worst case response time for all tasks, or we may be singularly interested in the worst case scenario just for one task, okay? Well, This is called critical instant. We need that in order to derive necessary and sufficient schedulability conditions. Sporadic tasks, I think we just said that. So sporadic tasks remove the strictly periodic periodicity assumption, but we allow a task to, so if this is the period, we allow the next job instance to arrive later than this period, not earlier, only later. It can arrive here, or here, or here, or here, or here, okay? So this is a sporadic task model. So again, we would like to guarantee that also in this case, when tasks have a minimum inter-arrival time, but not a fixed periodic time, they do arrive, they do complete, before their absolute deadline. Okay, I would like the task to complete before its absolute deadline. The point with sporadic task arrivals, if you guys remember what we saw, what we learned the last time about cyclic executive, about table-driven scheduling, remember those offline schedulers just filled a table in, okay, even a long or short table depending on the hyperperiod of the tasks, okay, and we managed filling in a table for 3 tasks, a table with 40, 50 entries, okay. But that setting was periodic, was strictly periodic. Okay. Remember, we were able to talk about a hyperperiod that repeats itself, this table that repeats itself, because the tasks were strictly periodic. Okay. What if I have instead sporadic tasks? Okay. What if I have inter-arrival times? For instance, it is often the case in real-time systems that I just know that two samples cannot happen before a given time, but they may arrive once and then not verify for seconds or minutes, okay? If it is an alarm, or if it is like, I don't know, some given input, or if it's a keyboard, okay? We know the data rate, the pressing keyboard rate that a user may have, okay? So if we know a minimum inter-arrival time, okay, we know how to specify a sporadic task. Well, since in a sporadic task, the inter-arrivals are not strictly determined, it is very difficult to use a cyclic executive in a timeless scheduler, okay? So I wouldn't know how to fill up a table if the task may arrive in different ways, right? So I wouldn't know how to fill my table in. We assumed in the timeline scheduling that the task would repeat periodically, and we were able to derive the minor cycle, delta, the major cycle, right? If this cycle can change dynamically, it is difficult to understand how to write a timeline schedule, okay? Instead, rate monotonic or other more event-driven scheduler work much better, because I can show you that the same example as before with rate monotonic would still work if tasks are sparsed a little bit more. If the inter-arrival of jobs happen not exactly at periodic times, but they are misplaced a little bit more, okay? So, for strictly periodic and also for sporadic tasks, for strictly periodic and for sporadic tasks, we can prove that a critical instant, so the worst case possible situation leading to the worst case response time of each task, is verified when A, all tasks arrive synchronously at the same moment, and B, each job is released as soon as possible. Let me clarify that. So a task is a sequence of jobs, right, with different periods of inter-arrival time. So I'm telling you that the worst case possible is when all tasks arrive together, okay, at the same point, synchronously, okay, simultaneously, and for a given task, the successive jobs are released strictly periodically. I'm telling you that even assuming a sporadic task arrival, okay, the worst case in the response time is verified when these jobs arrive as soon as possible, okay? So with the given minimum inter-arrival time. Is it clear? Shall I repeat? È chiaro? Sì. Italiano. Allora, io ho il caso periodico e il caso sporadico, dopo torno all'inglese, non abituatevi. Ho il caso periodico e il caso sporadico. Il caso periodico arrivano esattamente in maniera periodica, il caso sporadico questo è solo un minimo periodo di interarrivo, ok? Uno si può chiedere qual è il caso peggiore nel response time, quando mi arrivano strettamente in maniera periodica, oppure nel caso sporadico, magari scottando che uno lo posso mettere un po' più in qua, c'è qualche effetto che mi aumenta il tempo di risposta del task che sto guardando, ok? A me interessa capire qual è la configurazione di arrivi dei task che mi induce nel caso peggiore, che mi porta sul response time più grande di tutti, ok? Bene, io vi posso provare, non vi faccio vedere la prova, ma se volete, siete interessati la possiamo fare assieme, vi posso provare che il caso che conduce al peggior tempo di risposta per ogni task è quando tutti i task arrivano allo stesso momento e i job successivi di ogni task non sfruttano la sporadicità, ma arrivano esattamente in maniera periodica.
Dopo ogni T.
Esatto, dopo ogni T, esatto. La sporadicità mi permetterebbe di farne arrivare uno anche un po' dopo, no?
Quindi potrei sfruttare quella banda che mi dai in più per andare per eseguire un altro gioco, ad esempio.
Sì, ad esempio, sì, però questo appunto va nella direzione di ridurre il tempo di risposta per il gioco che riesce a eseguire nel frattempo, ok? Quindi va da sé che, cioè va da sé, andrebbe provato, comunque la prova non è così difficile, far vedere che nel caso esattamente simultaneo, no, di arrivi simultanei e strettamente periodici, è il caso che conduce al peggior tempo di risposta di ognuno dei task, dal task a più alta priorità until the lowest priority task. Ok? Is it clear now? Ok. So, from a schedulability point of view, the second bullet there, the sporadic model is the same as the periodic model. Okay? Despite the sporadic model allows you some more flexibility at task arrivals, so this flexibility does not influence the worst case situation. Okay? The worst case is still the one where tasks, where jobs arrive exactly periodically, okay, with strictly periodic way. So previous results for rate monotonic scheduling that we showed for periodic tasks like utilization bounds are also valid, they also hold for sporadic tasks. Okay? So what you see at the bottom is the same formula that we saw before. We could still use the utilization bound, only the I here is not the strict period, it's just the equivalent in the sporadic case, so the minimum inter-arrival time. Okay? So for us, this is the critical instant. This is the critical instant for rate monotonic. Every scheduling algorithm has a different critical instant. Every scheduling algorithm has a different critical instant. Okay? This is the worst case situation for rate monotonic. But if I were using a different algorithm, maybe this is not the critical instant, okay? I may found a different case where the response time is worse in a non-synchronous arrival or in a non-strict periodic arrival, okay? So the critical instant, so the worst case situation leading to the worst case response time, is depending on the scheduling algorithm that I use. For rate monotonic, this is a critical instant, okay? Okay, so basic assumption we have for the next slides. One task, so these repeated sequences of the same job are same jobs, so all of them have the same worst case execution time we call CI. Okay, all jobs have the same CI. The minimum inter-arrival time is constant for every job. And for now, we assume deadlines, relative deadlines, equal to periods, okay? So we don't introduce in the task model an additional parameters, which is the deadline, okay? We assume that the deadlines coincide with the minimum inter-arrival time of the tasks, okay? So deadline, so this is called implicit deadline model. And we assume that the tasks are independent, no synchronization, no dependencies, no arrows between one task and another one, okay, no resource constraints. So tasks are independent one another, okay? Well, this I mentioned to you before, but here it's written more explicitly. So I told you that among the whole class of static scheduling algorithm, static priority scheduling algorithm, what is the class of static priority scheduling algorithm? Is the set of all possible scheduling algorithms that I can use that assign one priority to a task and it will never change during the task execution, okay? Again, EDF is not a static priority scheduler because one task priority depends on the deadline of that particular job, okay? So later job has a smaller priority than the earlier jobs, right? So in static priority system, instead the priority of a task, tau 3, is always the same, okay? Nevertheless, the job of tau 3 that is executed, okay? So among the tasks, among the class of static priority tasks, rate monotonic is the best you can do. Okay? Among every possible assignment of priorities I can do to my task system, if I have 5 tasks, how many priority assignments can I make with 5 tasks? Who knows? Se ho 5 task, quanti... Se ho 5 task, quanti assegnamenti di priorità posso fare su 5 task? Posso dare al primo priorità, al secondo, seconda, terza, quarta, quinta, no? Poi posso tenere fisso il primo e variare gli altri, no? Quindi con 2 task quanti ne ho? 2 task 2, con 3? 6, con 4? Esatto, n factorial, okay? So, I have a huge space of possible priority assignments. I'm telling you, among these priority assignments, the best you can do is using rate monotonic, giving highest priority to the task with smaller rate, with a higher rate, so smaller period, okay? This is what I'm telling you here. So, if there exists a fixed priority assignment which leads to a feasible schedule for my task system, then rate monotonic is also able to schedule it. Instead, if my task system is not schedulable with rate monotonic, then no other priority assignment will be able to do so, static priority assignment. It may be the case that EDF allows me to schedule it, okay? Interrompetemi ragazzi se non capito per l'inglese o per il concetto, ok? Non abbiate paura. Mi rendo conto che non avendo mai ascoltato in inglese una lezione può... Ok, so again, we showed you before a utilization-based test. Here is another utilization-based test. Just, it does not only use the overall utilization of my task system, not the sum of the single utilization, it used the individual utilization of the tasks. So this is like a bound provided by a former colleague of mine in Pisa. He proved that the product of the individual utilization of tasks plus 1, okay? So this is like task 1 has utilization of 0.5, this is 1.5. Task 2, 0.2, this is 1.2. So 1.5 times 1.2. If this product is smaller than 2, then the task set is feasible, okay, with rate monotonic. This is a test which is a little bit better than the previous test that we saw before. Before we saw a test of this kind, where we used the global utilization overall, okay? We did not distinguish between the different utilization of the task. If we here make use of the information on the distinct utilization of each task, we can provide a better bound than that. So assume you just have 2 tasks, okay? Just to give you the perspective. So I'm plotting here the space of feasibility of task systems with utilization UI, U1 and U2, okay? So task systems composed of 2 tasks when they are feasible. They are feasible for sure when the sum of U1 plus U2, okay, is below a given bound, which happens to be, with n equal to 2, it happens to be 0.83, okay? This is like simple math, right? If I do U1 plus U2 equal to a constant, then it's a straight line in this space, okay? While this is a hyperbolic test, okay? Because if you plot it, and this is like U1 plus 1 times U2 plus 1, okay? Essentially, this is like hyperbole that is essentially strictly higher than the feasibility space that I had with the original test. If you go with 3 tasks, it's the same. You had a plane in one case and a 3D hyperbola that you had in the 3D space. So this is a slightly better test that you can use to discriminate in this space where I have a schedulable task set or not. Yet, it is just a sufficient test. Again, it is not necessary and sufficient. It is just a better test than the previous one. It was proposed a little bit later. Okay? Later, I will show you an exact test. Okay? I will show you an exact test, necessary and sufficient test. Okay? But before that, let's delve a little bit more on dynamic priority scheduling. Okay? For now, we assume a fixed priority, static priority scheduling. Let's move now to dynamic priority scheduling. And the most famous scheduler in this class is earliest deadline first. Okay? We saw it in the initial set of slides when we didn't have a recurring periodic task, but we just had a single task activation. Okay? And we showed that EDF was optimal. Okay? It was optimal because it scheduled every time the job with the earliest absolute deadline. Okay? And if a task set was feasible in my system, then it also was with EDF. Okay? It means we can prove that with EDF we can achieve full processor utilization. I told you that with the rate monotonic, which is the best static priority scheduler, we are not able to reach 100% utilization. Okay? So for n tasks, the most we can get is around 0.69 in the worst case, okay, in utilization. With EDF, I'm able to fully load my system until 100%. Okay? I can have full utilization, still guaranteeing all deadlines. Okay? Still while guaranteeing all deadlines. In the case that relative deadlines are equal to period or inter-arrival time. So this was like a task that was infeasible. We saw it before with rate monotonic. Okay? That was with rate monotonic. Okay? The lower priority task at some point gets interrupted and it misses the deadline. Okay? What would happen with EDF? With EDF, that task may continue executing here because its deadline is earlier than the deadline of the task released here. Okay? This deadline is earlier than this deadline. When this task requests a preemption, no, it cannot preempt because its deadline is later. Okay? This guy continues, then it passes this one. When this arrives, this deadline is here, so this continues, this executes, and all deadlines are met. Okay? Not only all deadlines are met, what do you notice also? There is something that improves.
You will have missed a deadline.
Okay, this is, we show that it doesn't miss the deadline, okay? So the visibility improves, okay? There is another thing that is better here. Yes?
Context switch.
Yes, we have less context switches, okay? So here, every time the high priority task arrives, we have a context switch. Here, we have less context switch than before, okay? You see? Actually, there is no context switch here, okay? No needed, okay? And not only better feasibility, but also smaller number of context switches, okay? And here, utilization 0.94, okay? But EDF is optimal, so if there exists a feasible schedule ever, in every possible schedule, not just restricting to fixed priority or dynamic priority, any kind of scheduler that you can come up with. So if it is feasible, your task set, then it is also feasible with EDF. On the contrary, if your task set is not feasible with EDF, there is no possible scheduler you can use to make it feasible, okay? So EDF seems to be the best choice to use. Single processor system, deadline equal to period, independent tasks. The world out there is not this world, okay? So these are simplifying assumptions. Tasks are depending with each other. We have critical sections, shared resources. We have multiple cores, not just one, okay? And deadlines may be different than periods, okay? But in the ideal world, okay, where the real-time literature was focused in the early years, okay, EDF was the best you could use. Okay, single core, independent tasks. Okay, no shared resources, and deadline equal to period. How can I prove the optimality? Well, it's the same proof that we are used to. Okay, only here I may consider that preemption may arise. Okay, so you don't just have a continuous execution of tasks. A task may, in a possible schedule, which leads to a feasible solution, it may decide to preempt multiple times my task. Okay, so this is again the strategy proved by contradiction. What am I doing here? So I would like to prove that EDF is optimal. How do I prove that? By contradiction. I assume that there exists another scheduler which leads to a feasible schedule, while EDF is not. Okay, this is my basic assumption. I assume that there exists another schedule which is different from EDF, which leads to a schedulable condition, so all tasks finishes before the deadline, while EDF misses the deadline. Okay, this is my assumption. Okay, okay. With this assumption, I lead to a contradiction. So I will show you that I do manipulation, and I will show you that EDF does not miss. Okay, I reach a contradiction. This allows me to prove that EDF is optimal. Okay, so the proof by contradiction. This is the third time I'm telling you. So by contradiction, I would like, my claim is to assume that, I would like to assume that, to prove that EDF is optimal. What does optimal mean? That whenever a task set is feasible, it is also feasible with EDF. Okay? EDF is optimal whenever a task is feasible, it is also feasible with EDF. How can I prove this claim? By contradiction. So let's contradict this assumption. EDF is not optimal. So there exists a different schedule, sigma, different than EDF, okay, for which this guy leads to schedulable, while EDF not schedulable. Okay? Okay? So this is the assumption that I made. Okay? This is my contradicting assumption. Okay? So here is my assumption. Here is sigma. Here is the schedule that leads to all deadlines be met. Okay? All deadlines are met there. Okay? Now what I do from this contradicting claim, or the contradicting assumption, I do some manipulation, okay, and I reconstruct the schedule of EDF. And while doing this manipulation, I can show you that the finishing time of the task will only decrease. Okay? So I'm telling you, I'm showing you that no, this is not true. Also EDF is schedulable. Okay? So in this case, I showed you that I reached a contradiction. Okay? I assumed something the contrary of my claim, and I was led to a contradiction. This is a typical strategy proof that we use in the real-time community to prove things, not only in the real-time community. This is a proof by contradiction. Okay? So let's do the proof. Assume you have a schedule different than EDF, which meets the deadline while EDF doesn't. Okay? So let's transform. Let's transform our task. Start from the beginning. Okay? Start from the beginning. As long as you have the same scheduling decision that EDF would take, fino a quando le stesse, no, decisioni di scheduling uguali a quelle che EDF prenderebbe, okay, as long as I have the same scheduling decision, this is the latest deadline, but there is no task around, okay? So EDF would have taken the same decision. Here, a task with an earlier deadline arrives, so EDF would schedule this one, okay, also this schedule would schedule this one, okay? Then this task arrives, which have an earlier deadline, okay? Has an earlier deadline. So this is a point in which I'm taking a different scheduling decision than EDF. EDF here would have scheduled this guy and not this guy, okay? So here is just a concrete example. In a strategy proof, you must say, I go to the first point where my schedule, my allegedly optimal schedule, takes a different decision than EDF. Okay? I go to the first point where my schedule takes a different decision than EDF. Then what I do? I take the slot where the decision is different from that of EDF. Okay? And I do this switch. Okay? This is an argument that you guys are getting used to, right? So, with this switch, what has happened? With this switch, I can show you this, that feasibility is preserved. So if I assume that the original schedule was schedulable, so that all tasks were meeting deadlines, so that all tasks were finishing before the deadlines, by this switch, it can never happen that they will now miss the deadline. Okay? Switching them, it can never happen that they become infeasible. Okay? That they will execute over the deadline. Why is that? Because this guy, okay, executes earlier. So this is FE, okay? This is FK prime. So, okay, by moving it here, it's okay. The finishing time of K goes here, okay? While the finishing time of this goes earlier. How do we prove that feasibility is preserved? So this guy goes earlier, so it cannot possibly be worse than before, right? So I'm advancing his execution. So this guy is okay. I just need to prove that by putting this guy later, it will not miss the deadline. So where this guy will finish executing. So it will finish here, where this guy was finishing before, okay? So Fk prime equals Fe, okay? Goes here. But we know that Fe, the finishing time of this guy before, he was meeting the deadline. He wasn't missing the deadline, okay? So we knew that Fe was smaller than its deadline, okay? We knew that the finishing time of this guy was earlier than this deadline, right? But we also knew that this deadline was earlier than this deadline. Okay, we knew that the E was earlier than the K by the assumption we made, right? So again, let me repeat. So EDF, first decision different than EDF, okay? It means that a task with later deadline is scheduled instead of a task with earlier deadline. So let's switch them, okay? So this guy which have an earlier deadline and this guy have a later deadline, I switch them. The guy that goes before cannot possibly has a worse response time, okay? The guy that gets later, okay, yes, it will execute later, but still its finishing time will be before than the deadline of the first one by assumption, which is before the deadline of the other task by assumption, okay? I reached a situation in which I still preserved schedulability.
But why tau k preempts the task in the middle?
This is just assuming a different schedule. It can be whatever schedule. It can be a random schedule, okay? So we are assuming that there exists any schedule that leads to a feasible situation while EDF is not.
But
okay?
in this case, we have tau k finishes after Fe.
Here it finishes, right?
No, because the task in the middle has an earlier deadline.
Yeah, but I'm not, so in the existing schedule, so is this schedule different than EDF? So sigma is a schedule that I assume exists different than EDF. It can do whatever it wants. It can do like execute randomly stuff here. So you don't need to execute like EDF task. Non devi replicare lo schedule di EDF. Io sto assumendo che esiste uno schedule che qualcosa fa e alla fine i task finiscono prima delle deadline. Okay? Mentre EDF non lo fa, no? Quindi by contradiction. Se io faccio vedere, parto da questo schedule che fa un po' quel cavolo che vuole lui, magic scheduler, ok? Io inizio dall'inizio. Qual è il primo punto dove la decisione è diversa da quella di EDF? Qua, ok? Ad esempio in questo caso qua, ok? Allora cerco di riportarmi alla cosa che fa EDF, ok? Almeno facendo scambio via scambio, io ti dico per ogni scambio io ti faccio vedere che non posso fare peggio di quello che stai facendo te. ok? Cosa vuol dire non posso fare peggio? Vuol dire, intanto quello che porto indietro ovviamente non può essere peggio. Quello che porto avanti comunque finirà prima della sua deadline. Perché? Perché la sua deadline, come abbiamo detto di F, è dopo la deadline di quello che è scambiato, che comunque finiva in tempo. Quindi quando lo faccio e lo porto avanti, anche questo nuovo finirà in tempo prima della sua deadline.
Ok, ma comunque non stiamo ancora parlando di IDF.
No, questo non è ancora EDF. Dopo questo switch non è ancora EDF. Vi ricordate come abbiamo fatto negli altri casi, no? Questo è solo il primo step. Dopo io continuo a cambiare, io posso ripetere lo stesso argomento over and over until I replicate the EDF schedule and I reach a contradiction. Ok?
Io quindi prendo il task che ho la deadline che finisce prima e faccio lo switch con un altro task che iniziava prima.
Allora io cerco il primo punto dove c'è una decisione diversa da EDF, no? Qui cosa avrebbe fatto EDF? Avrebbe simulato questo, giusto? Invece di questo, no? Quindi cerco, no? Guardo, fino a quando no, una decisione diversa da EDF, per adesso fino a qua, rispetto a questo, no? E lo scambio, ok? Dopo non ho finito, dopo non ho ancora EDF, come ha detto il vostro collega, devo andare avanti, no? Qui ho detto solo che la feasibility è preserved, ok? La feasibility è preserved. I transform sigma to sigma prime, okay, and the feasibility is preserved. As you're used to, we repeat that over and over until we get to a feasible condition, okay? Feasible to the EDF schedule itself in a feasible way, okay? It's a simplified proof, okay? The real proof would be a little bit longer with all these changes, okay? Okay, so I can claim, since EDF is optimal, I can prove you, it was in D'Artuso's paper or in your Leyland paper, that I can reach until the full utilization of my task system, okay? I can prove you that EDF is able to schedule until a least upper bound of 1. So for EDF, a necessary and sufficient schedulability condition is computing the utilization, seeing whether it is 1 or less schedulable, more than 1 non-schedulable. Okay? Much easier. I'm able to exactly discriminate which task systems are schedulable from those that are not. Okay? In the simplified world, single core, no dependencies, and deadline equal to period. Okay, here is like the behavior between rate monotonic and EDF or other task systems. This is again shows what we saw before. We may have deadline miss with rate monotonic, utilization here is more than 1, and we also have a higher number of preemptions with rate monotonic than with EDF on average, okay? Not in the worst case. But on average we have a higher number of preemption and context switches with rate monotonic than we have with EDF. Here are the preemptions that you have with rate monotonic below the preemption that you have with EDF. So with rate monotonic you have 5 preemptions, with EDF you have just 1. Okay? Essentially with rate monotonic, with fixed priority, the highest priority task, when it arrives, it always preempts. Okay? You can see that it's never delayed. Okay? When it arrives, it always preempts if someone is executing. Okay? With EDF, this is not the case. The task with smaller period can be delayed a little bit to allow the higher priority task to continue executing. Okay? So why using EDF? Why using rate monotonic if EDF just works better? Okay? So EDF is more efficient, so provides you higher schedulability, and it has less context switches, okay? So why not using just EDF at all? So, well, rate monotonic historically, and a static priority system historically, have been much more used in the practice, okay? Despite EDF is better, almost all operating systems provide you a fixed priority, a static priority schedule, scheduler. Only few of them provides you an EDF-based scheduler. Okay? What is the reason? Maybe the reason is that with EDF you need to keep track of deadlines, absolute deadlines. You have to dynamically keep track and update timers related to deadlines. Okay? So this is something that adds a little bit of overhead. Today it's negligible, but a few years ago this was not negligible. Okay? And also with fixed priority, with static priority, it's more predictable to execute very high priority critical activities. As I told you, assume you have a very, very critical activity, here, okay, with the rate monotonic, the highest priority task is something that I need to execute exactly at that moment, despite whatever workload I have below, okay? Even if this tau2 would execute for 1,000 time units every 10 time units, so would have a utilization greater than 100, this task would still meet its deadline. I will repeat. Assume this guy, tau2, needs to execute every period for 1,000, okay? So it definitely will miss the deadline forever and ever. This guy still will not miss the deadline with that fixed priority. What would happen with EDF instead? Assume you have a second task that needs to execute forever every period. What would happen to this guy? Would it miss the deadline or not? Yes. Okay? So in case of overload conditions, okay, overload condition, when the sum of the utilization is greater than 1, for instance, I have a misbehaving task here, okay? This task here has a deadline here, and this guy has a deadline here. So if this guy continues executing, it misses the deadline, but also this guy misses the deadline, and the next one misses the deadline, all tasks miss the deadline, okay? While with fixed priority, the highest priority one is more predictable. At least the highest priority one will not miss the deadline, okay? Think about some safety critical task, okay? At least the high priority task, I'm guaranteed that is guaranteed to execute, okay, despite overload conditions, okay? So these are reasons that are in favor of rate monotonic or static priority in general. It's more predictable during overloads, okay? Still, we have ways, even with EDF, with a deadline-based scheduler, to isolate unpredictable workloads, okay? We will see them in future classes. Okay, so let's remove a little bit of the ideal world. Let's start with removing the assumption on deadline being equal to periods, okay? So we started with periodic and implicit deadline, then we moved to sporadic and implicit deadlines. Now we are moving to sporadic with deadlines different from periods, okay? So the model is this one. This is a recurring task that has a minimum inter-arrival time, so the next job may arrive either here or at later points, but the deadline of the job is not necessarily equal to the inter-arrival time. The deadline can be smaller or larger or smaller, okay? When it is only smaller, we call it a constrained deadline model. When it is arbitrary, it is called arbitrary deadline model, okay? So we basically added to our task model, instead of it being CI and PI, it is now CI, PI, DI, okay? I add a relative deadline to my task model, okay? So, which scheduling algorithm could I use? I can still use some static priority scheduling algorithm. In that case, I'm telling you that instead of using the period to discriminate the priorities like we did in the rate monotonic, it is better to use the relative deadline. I better use the relative deadlines to discriminate priorities. The best algorithm here is called deadline monotonic instead of rate monotonic. Okay? Deadline monotonic essentially assigns higher priority to the task with smaller relative deadline. Why relative? Because we are in the world of static priority scheduler, okay? I cannot use dynamic deadlines. I cannot use absolute deadlines, okay? I use relative deadlines, which is the same for every job of that task, okay? If I move to the dynamic world, again, it's EDF, okay? Nothing changes. Again, it's EDF that essentially assign dynamic priority based on the absolute deadline. Nothing changes here. only the fixed priority one changes. Instead of periods, I use relative deadlines. Okay? Well, you remember, right, what we did for the schedulability test for rate monotonic. For rate monotonic, we first showed a utilization-based schedulability test. Okay? The Euler bound, so this n times square of n 2 plus 1, minus 1, sorry. That does not hold anymore here. You cannot use the utilization as a parameter to discriminate whether a task set is feasible or not in a model where deadlines may be different from periods. Okay? For instance, I can tell you that I have tasks, it's not in these slides, I can tell you that there are tasks with a utilization close to 0 which are still not schedulable in this model. Can you guys tell me? So, please tell me, find out a task set where I use this model, CI, BI, TI, and that the overall utilization tends to 0, but deadlines are missed with deadline monotonic. Take your time, think about it. It's enough to have 2 tasks, okay? It is sufficient to have 2 tasks, okay? With some period, deadline, and execution time, okay? I'm asking you, what is the task set? Take your time, think about it. So what is a task set with 2 tasks, where each task have a negligible utilization? I take my scheduling decision based on the relative deadlines, and I still miss a deadline. Now look at the slide. The slide talk about something different. The slides are not interesting to solve this problem.
After with a constrained deadline or?
Constrained deadline, yes. Yes?
The first CI is equal to the DI, and the second.
So this guy have a CI equal, so this one
Yes.
has a CI,
that is equal to the relative.
okay, like this,
Yes.
okay, and this guy
Other,
has a little bit larger one, right? And then the periods,
the second of the deadline.
second,
The second relative deadline of the task.
what do you mean the second value? Like the period here, what if I move it a little bit more? Or more? Or more. Or to infinity, right? Right? So, what happens here? So, just to summarize, this guy have execution of 2, okay, this is the CI of 2, with a relative deadlines of 2, and a period of okay, well this guy has an execution time of 2, a deadline of 3, and a period of the same as before, okay? What is the utilization of this task? 2 over infinite plus 2 over infinite, it tends to 0, right? Okay? So, still deadlines are missed, okay? But the utilization goes to 0. Why am I telling you that? And it's good that you guys found it out alone. Because when you take a model where deadline is different from period, you cannot use the utilization as a meaningful value to discriminate where a task is feasible or not. Okay? Because there are task systems with utilization 0 which are not feasible, so there is no point. So list upper bound is 0, so it's a totally useless test if I were using the utilization as we know it. Okay? It is better, I tell you, to use a modified utilization, so using the relative deadlines instead. Okay? I could use the relative deadline instead because this system, for instance, it has 2 over 2 is 1 and 2 over 3, okay, is 2/3. So the sum of the modified utilization would be greater than 1, and that could be used as an indication for your task to be infeasible, okay? So modified utilization greater than 1. But, now the slide. If I were using the modified utilization, again I may incur in some problems. So the modified utilization bound is not so indicative too, because I'm showing you here a task set, a very simple one, where the first task executes for 2 out of deadline of 3 every something, while the second one executes for 3 with a deadline of 6 every 8-10 units. So if you sum up the modified utilization, it gets above 1. Okay? I can ask you another problem. Yes, I would like to get fun. So let's try to find something opposite than before. Let's try to find a feasible task system with deadline monotonic where the modified utilization gets to infinite and the task set is schedulable. All tasks meet their deadline and I have a utilization going to infinite. Okay, think about it at home, okay? Because you need to know a little bit of theories in the math. So, what? Anyway, think about it at home, okay? If you have a solution, it is not in the slides, so you're free to investigate for yourself. Remind me next time, I will tell you the solution, okay? Again, it is clear the problem, right? So, tell me a task set with potentially infinite number of tasks, okay, that have a utilization arbitrarily high and it still meets deadline. Okay, it has a modified utilization arbitrarily high and it doesn't miss any deadline. Okay, that's a nice problem to think about. Okay, now enough about EDF. Let's go back to rate monotonic. Okay, enough about EDF. EDF is nice when the tasks have deadline equal to period. When deadlines are different from period, we don't have a good test to use. We are going to identify it later, okay? We do have a test to use also when deadlines are different from period. I will show you later. But what we had in the static priority world, we have a utilization-based test. It would be conveniently used for when tasks have deadlines equal to period. But nevertheless, there was this problem of okay, erase it, this black region between the utilization list upper bound and a utilization equal to 1. So I would like to show you a necessary and sufficient test for rate monotonic or static priority in general, okay, rate monotonic or static priority in general, that holds also for discriminating this gray region, okay? And by the way, you can use that test, this test, also for this more complex model. Okay, let me repeat. When you assume deadline different from periods, I told you you cannot use the utilization rate test not for EDF nor for rate monotonic and fixed priority. Okay, you cannot use efficiently the modified utilization test. In that case, so what shall we use? Let's start with the fixed priority scheduler. With fixed priority scheduler, I will tell you what to use, and by the way, it is the same test that is exact, so that allows you to discriminate in the gray area between the list upper bound, either the ULA list upper bound or the hyperbolic bound, and the necessary condition of utilization smaller than 1. How does it work? It works with a very basic, simple assumption, consideration, that the response time of a task is given by its worst case execution time plus the amount of interference it receives by higher priority tasks. Let me repeat. If I need to compute the worst case possible response time, I need to factor in how much shall I execute for my task, my job, and how many times will I be interrupted to execute higher priority tasks. Do I need to take care about lower priority tasks? Why not? They won't execute, right? They have a lower priority, okay? So in the interference, this I factor there, I shall not consider lower priority tasks, okay? I'm not interested. I'm just interested in what I will be executing, and higher priority tasks will preempt me and execute, okay? I'm not interested in what do lower priority tasks do. When will I be interested also in what lower priority tasks do? This is important for future classes. When I will remove the independent task assumption. When I will use semaphore, mutases, logs on shared variables, shared resources. I may have a lower priority task that is holding a log, a semaphore, and will cause me some blocking, okay? Because I need to access that semaphore, but the lower priority task has that semaphore, okay? This is one of the root causes for some big failure in aerospace mission, the Mars rover, and many other cases, okay? This is a very subtle problem that is difficult to identify if you're not in this domain, if you're not used to play with the things, okay? But it's definitely something that may happen. A lower priority task that holds a semaphore, it introduces some blocking on higher priority tasks that eventually miss the deadline, okay? In the Mars Pathfinder, that led to repeated deadline miss, and the rover was repeatedly bootstrapping again and again, and the connection was lost, okay? So, Ci plus Ii, and when I compute this Ri, so seeing it like this, it's simple, but it will not be as simple to compute this Ii, but once I have this response time, I basically need just to compute whether it is smaller than or equal to the deadline, okay? Once I computed the response time, actually the worst case response time among all possible jobs and configuration, arrival, and whatsoever of my task, I compare it against my relative deadlines, okay? And I check whether it is less or not. If it is less, feasible. If it is not, infeasible. Exact test, okay? Response time analysis by Odsley in the 90s. So, the problem is not computing CI, the problem is computing the interference, okay? So, assume that I just have two tasks here for simplifying things, okay? Deadline different from periods, I told you that this is a test that is exact, but also allows you to be used in the deadline different from period setting, okay? So, lower priority task, higher priority task. Execute, preemption, response time, okay? It still holds the theorem which says that the worst case response time of a given task is found when it arrives simultaneously with all higher priority tasks, okay? And all tasks, all jobs arrive as soon as possible, so with the inter-arrival time equal to the minimum inter-arrival time, okay? Sporadic model, deadline different from period, critical instant, okay? So it is sufficient. I don't need to consider all possible arrival around, okay? I just consider the situation in which these tasks are compacted out at the minimum inter-arrival time and both tasks arrive together. Both or more tasks arrive together, okay? I don't need to consider lower priority tasks when I compute the response time of this guy here, okay? Then, how do I compute this response time? Okay? I told you, is computation time, so this, okay, this is CI, okay, plus the interference. What is the interference? The interference is whatever fits the response time that includes the execution of the higher priority tasks. Again, the interference in this region here is the amount of execution of the higher priority task within this window, okay? What is the amount of execution of the higher priority task within that window? So what is the amount of execution of the higher priority task in a window of length R, how many times, how many jobs of the high priority tasks execute within R time units? Well, it's easy to find. It's Ri over Ti ceiling, is the ceiling of Ri over Ti. Parte intera superiore il response time su periodo del task ad alta priorità. Why? One period, one execution. One period, another execution. One period, okay, parte intera superiore, another execution. Think a little bit why this holds. So if my response time starts here, okay, no, it shall include this guy before. Once it arrives, it's a step function, okay? This is a step function that has a step, has a stair, every time I reach Ti. So this is a staircase function that essentially does start from 0 and goes immediately to Ck. At the next period, it boosts another Ck. At the next period, it boosts another Ck, and so on. So every time I reach a new activation of a higher priority task, I have a step of plus Ci, okay? Plus Ck, sorry. So essentially, I'm here assuming to know this R, and I compute how much will I interfere in this R window, okay? Yes?
In this scenario, we have just one decay.
Yes.
Just one.
Yeah, if I have more, it will be the sum
Okay.
of all higher priority tasks, okay? We are reaching that. So, okay, if we have more tasks, it is essentially the sum extended over all higher priority tasks. This is essentially the sum starting from k equal to 1, the highest priority tasks, until the tasks with priority right above me, okay? If I have 4 tasks above me, it's the sum of all 4 tasks, okay? And for now, so far, so good. So that means that your response time is, again, your computation time plus the interference as we computed it before. Okay? Is it clear for now? So far, so good. What is the problem of that formula? Say again?
We have to know when they are at a time.
Exactly. Sorry, we have to know the arrival time. No, we do know the arrival time.
Yeah,
The response time, you mean. Okay, yes. So we don't know the response time. So why can I use like math rephrase, math manipulation just to derive R from there? Okay, if instead of the ceiling I had something different, then I could manipulate the formula to derive R. Yes.
You can also keep the ceiling and having a majorative or minorative.
Exactly. Are you a student or? Well, what your colleague says is that you could take out the ceiling and use an upper bound or a lower bound to that magnitude here. Well, we are not interested in that. So without losing precision, are we able to derive Ri from this formula, taking it out, manipulating? Well, I'm telling you, not. We are not able to do so because this ceiling, okay, is a nonlinear function and it's difficult to take it out, okay, unless you lose some precision, okay. If I take out the ceiling, it will be something that will be smaller than what I assumed here, okay. So if I take out the ceiling, I just use parentheses, okay, this is a magnitude that is smaller than the original factor with the ceiling, okay. If you do that, you lose precision, okay. So how can we solve this problem? Well, we solve it iteratively. We solve this problem iteratively. Okay? Response time analysis solves this problem by iteration. I start with a tentative response time. So the response time of I at step 0, my initial guess for the response time is, what if the response time is CI? Okay, so my response time shall be at least CI because it's what I need to execute, right? So let's assume executing for CI, okay? Then what do? I compute whatever would happen here if I replace this Ri with the CI, okay? I compute, what is the result? Is it CI? Then I'm done. It is something that is different from CI, it is for sure greater than CI, I can prove that. Then continue putting it again here. Compute, is it the same as the previous step? No. Continue putting here. Is it the same? No. Continue. Is it the same? Yes. This is your exact worst case response time. This is the general formula. So basically the response time at the next step, step plus 1, is what you compute by putting the response time of the previous step in this formula. Okay? That's a peculiar way to solve this kind of recurring formula in an iterative way. Okay? Basically, I continue iterating until the response time that I get from here is the same as the response time that I inserted here. Okay? That's a strange way to do stuff. Well, it would be convenient to do an example together. Or we can use some of the tasks that we have there. Yeah, this one, for instance. So here we do have a task with execution time 2 with a period of 10. Okay? 2 every 10. With a deadline of 4. While the second one has an execution time of 3, the period of 8, and the deadline of 6. Okay? So I start with the response time analysis. I use the formula that I have here. Okay? Let's start with you have to repeat that formula for each task. You first derive R, you compare it against the relative deadline. So I start with the highest priority task. Okay? Tau 1, R1, so this is tau 1, and this is tau 2. Okay? R1 at step 0, I guess it will be 2. Okay? Let's put it in the formula. So let's see, what is R1 at step 1? So I put Ci, which is 2, plus the sum over all higher priority tasks of this term. How many higher priority tasks do I have here? No. Okay, this is the highest priority task, so this is plus 0. 2 equal to 2. Response time of tau 1 is 2. Okay, so R1 equal to 2 less than or equal to the deadline. Okay, for now, the highest priority task is schedulable. Did I finish? No, I have a second task to check as well, right? Which will be a little bit more difficult. Little bit. Okay? So, R2 at step 0, I initialize it to C2, okay? Which is 3, okay? Then, R2 at step 1 is 3 plus the sum over all higher priority tasks of their interference. What is their interference? Is the tentative response time, which is 3, divided by the period of them, which is 10, okay, in a ceiling, times the amount of their execution, which is 2, okay? This is actually this formula, okay? Ci, which is me, which is 3, plus my guess response time, which is 3, over the higher priority task period, which is 10, in ceiling, times the execution time of the higher priority task, which is 2. Okay? So let's compute that. So 3 over 10, ceiling is 1, so this is 3 plus 2 equals 5. Is 5 equal to 3? No. Then what shall I do? I shall open another one here, R22 equal to Ci, which is 3, plus the same as before, but using 5 now, over 10, blah blah, 2 equal to 3 plus something which is 1 plus 2 equals 5. 5 equals 5, so R2 equals 5, which is less than or equal to 6, which is B2, is schedulable. Okay? Let's check back what we have there. So I'm given a response time, worst case response time of the first task of 2. Yes, essentially it is. This is the worst case critical instant, okay? Right? And I have a worst case response time of tau 2 of 5. Yes, this is essentially the worst case response time. Also here is 2, 5. Here is 3, 3. So the worst case response time is 5. Okay? If you have multiple tasks, okay, you should go on with that. Okay? One of the exercises in the written exam for the oral part, the last exam for the oral part, would be solving a response time analysis of this kind. That could be solving a response time analysis of this kind with 3 or 4 tasks. Okay? Basically, you could either apply the formula or you could also build the schedule. Okay? Essentially, this iteration, if you check, what does the iteration do? So this iteration, essentially, well, it's best if you have a better task set. Here. Essentially, what it does, it essentially guesses the complete time, the completion time. First starts with 3. Okay? If in this 3 you have an arrival of that task, then you increase it. Okay? Sorry, it's 4. So you start with 4. If in 4 you have the arrival of one of these tasks, yes, we do have. We do 4 plus 2. We go to 6. In 6, do we have a further arrival? Yes. So it's 6 plus 2. It goes to 8. Okay? And so on. So basically, in this way, you may derive what is the best, the worst case response time. Okay? Yeah, 4 plus 4 is 8, so it's here. So this is exactly the worst case response time. You may finish without considering whatever else is later. So the response time analysis, you don't need to go on and on and on and on to check all possible cases. The first time you have a convergence here, so you reach the same result, you may stop. What does it mean? That you're computing essentially the response time of just the first job. You don't need to compute the response time of the second, of the third, of the fourth, of the fifth. Okay, why is that? Because there is a proof that the critical instant is this one, and the worst case response time is given by the first job of that task after the synchronous release. Okay? It is not just that the synchronous release and periodic release leads to the worst case response time, but also that that response time is given by the first job in that case. Okay? This always holds when you have implicit or constrained deadlines. It is not the case when you have arbitrary deadlines, so when you may have deadlines greater than the period. Okay? We are not so much interested in that model. But when deadlines are greater than periods, the worst case response time can be given even later, by later jobs. Okay? We are not much interested on that here, unless you need to publish in the real-time scheduling literature, which is not the case. Okay. I don't know about you, but I'm quite tired. What time is it? Yes, 5:30. What about stopping here? Okay. Let's continue on Friday when you will have your colleague there that will help you in the exercises. Okay. You know what we will do on Friday?
Probably on Friday we will start by a little survey regarding the programming model that we are using, in particular the programming rules that we will programming style that you have to follow in the program to pass the exam. If you don't follow this programming style, you will have 0 from the program. After that, we will see a start from a very simple library we use, which is the Allegro library, that will be used for the graphical part of